Hi everyone, I'm Zhan from Princeton University, and I'm going to talk about quantum log-space algorithm for powering matrices with bounded norm. This is a joint work with Girish and Matrices. Let's start with a fundamental principle in quantum computation, the deferred measurement principle. It states that in a quantum circuit, with intermediate measurements, you can defer all of the intermediate measurements to the end of the circuit, and it works as follows. First, we add ancillary qubits, each corresponding to an intermediate measurement. Then we replace each intermediate measurement with a C0 gate. Finally, we measure the ancillary bits at the end of the circuit, and the outcomes and effects of these measurements are the same as the original intermediate measurements. We can see from the illustration that the number of additional ancillaries is exactly the number of intermediate measurements that we want to defer. In particular, let's say we have a circuit with intermediate measurements of polynomial time and logarithmic space. Here, time means the number of gates in the circuit, and space means the total number of qubits, including ancillaries. After applying the deferred measurement principle, we turn it into a circuit without intermediate measurements of polynomial time and up to polynomial space. So the time will not increase by a lot, but the space does get an exponential increase. So the natural question to ask is, can we defer intermediate measurements with both time and space efficiency? And here we give a positive answer. We show that starting from a circuit with intermediate measurements of polynomial time and logarithmic space, we can efficiently construct a circuit without intermediate measurements of still polynomial time and logarithmic space, and it has polynomially small error compared to the original one. Before we move on to the statement of our main result, let's first go through some basic concepts in quantum computation. A quantum channel is a completely positive trace-preserving map over the density matrices. Each quantum channel has a natural representation, which is a matrix that maps the vectorization of the input density matrix to the vectorization of the resulting density matrix. A quantum channel is unital if it maps the identity matrix to the identity matrix. Unital channels include unitary channels, mixed unitary channels, and all of the measurements, basically everything performed on a quantum memory. We also know that a quantum channel is unital if and only if its natural representation has spectral norm at most 1. Now, a quantum algorithm is basically a series of quantum channels applied sequentially. So for a quantum algorithm with time t and space s, we can describe it as T complex matrices being the natural representations of the channels, and each of them has dimension 4 to the s by 4 to the s. For a quantum decision algorithm, which outputs either 0 or 1, we can always assume that at the end, only the first qubit is measured. Therefore, the probability of this algorithm outputting 1 can be written as the following expression. It is the trace of the product of the final state with pi1, which is the projection operator on the first qubit that projects to the 1 state. We can rewrite this expression with the natural representations of the channels. It becomes our large product containing the vectorization of the projection operator, a chain multiplication of all the natural representations of the channels, and the vectorization of the initial state. Now, if we let A to be this large block matrix containing all of the natural representations at an off-diagonal position, then we can further rewrite the output probability using the tth power of A. Also notice that when all the channels are unital, this matrix A has spectral norm at most 1. That's how we connect the problem of simulating quantum algorithms to the problem of computing the powering of a matrix with bounded norm. So here is our main result. Given a complex matrix A of dimension n by n with spectral norm at most 1 and a number t polynomial in n, we can compute a to the tth power quantumly with only unitary gates, and the measurements at the end, of course, in polynomial time and logarithmic space with polynomially small error. In comparison with classical algorithms, we only know how to do that with either super polynomial time or with polylogarithmic space. This means that we can simulate up to polynomial accuracy any Logspace unital quantum algorithm with Logspace unitary quantum algorithm. There are several implications for this result. First, it implies that the deferred measurement principle can be done efficiently in both time and space, as we mentioned above. It also provides a quantum analog of the result on classical reversible computation. Long, McKenzie, and Tabb showed that every classical computation can be simulated by space-efficient reversible computation, and we show the same applies to computation on quantum memory. Independent of our work, Pfefferman and Ramsgrim proves a more general result, providing simulation of any Logspace quantum algorithm with Logspace unitary quantum algorithms. So their results apply to algorithms using both quantum and classical memories. Our result also has an implication on quantum learning theory. We show that you can efficiently simulate every quantum learning algorithm with classical learning algorithm if and only if you can efficiently simulate every quantum decision algorithm with classical decision algorithms. That is, either they are both simulated efficiently or there are separations in both scenarios. Also, because we already know that quantum log space is contained in classical log square space, it implies that unconditionally, quantum learning algorithm can be simulated classically with some non-trivial time and space shown here. So here is an overview of the proof of our main result. First, we construct a unitary quantum circuit that contains the target matrix A as a block. This step is done by Hamiltonian simulation. Then we show how to repeatedly apply the circuit to get the powering of A, and this only involves a simple trick. Notice that in the expression of the upper probability, the vectorization of the projection operator is not a unit vector, although the final part, the vectorization of the initial state, is indeed a unit vector. So we have to rescale the probability using Grover rotations. This provides simulation with constant error. And finally, we show how to scale the accuracy up to polynomial using already known amplifications and the deferred measurement principle that we get from above. Notice that every step here is done efficiently and unitarily. And now we will briefly go through all of them. The first step is very well known. Given the matrix A, let H be the Hermitian matrix containing A. We can then construct a unitary matrix based on H, which in turn contains A as a block. The implementation of this unitary matrix is done by Hamiltonian simulation, whose framework dates back to Harrow, Hasidim, and Lloyd. And Tashma shows how to execute it to meet our requirements. We then permute it to get a unitary V with A on the top left corner. Now we have the unitary matrix A. We cannot directly apply V many times to get the power of A because the rest parts of the matrix are messed up. So here is the simple trick. We first apply V once, and we add n auxiliary dimensions and permute these dimensions to make them align with V. Then we apply V again and rinse and repeat for t times. This process will multiply the dimension by a factor of t, which is merely a log t increase in space. So far, we have already powered the matrix, so we can also compute any bilinear form with it on any unit vector. But when we apply it to simulate a unital quantum algorithm with output probability p, we only get a unitary algorithm with probability p over square root of n. Because as we said, the vectorization of the projection operator is not a unit vector. Instead, it has length about square root of n. Actually, the angle of the final state and the zero state is a fixed number depending on p and n. Therefore, we can apply the Grover rotation, which is first reflect according to the zero vector and then reflect according to the v vector. And this will increase the angle by about twice that fixed angle. So after about square root of n such rotations, we can reach a state that gives output probability about sine square of p. The exact expression of the output probability here does not matter as long as it is constantly close to the original probability p. So up till here, if we want to simulate quantum algorithms that decide the language with bounded error, we have already done. And this error for decision problems can be further reduced to exponentially small by a result by Pfefferman et al. In 2016. But it takes some extra steps if we want to get really close to the original output probability. The way we do that is to actually compute every single bit of this probability p in binary representation using Marriott-Watrous amplification. Then we can prepare a brand new final state to be measured with this value of probability in hand. The problem is that the amplification process introduces new intermediate measurements. The interesting thing is, since each bit of p can be viewed as a decision problem, we can actually defer these newly introduced intermediate measurements efficiently with what we already have for decision problems. It's kind of tricky, but in a way, we used our own results to improve themselves. There are still tons of other details in the paper, but we are not going to cover them here. That's all for this talk, and thank you for listening.